Hi, my name is Lillian Wilson-Wade, and today I'll be discussing Lab 4. In this lab, we were tasked to examine the motion of a mass oscillating on a spring. In the past, we've predicted the motion of objects that are moving at a constant velocity and that of objects affected by a drag force, but this lab is different because obviously the mass is oscillating in an arc on a spring, and we'll also be using the energy principle. The key principles to understanding this law are the energy principle and Newton's second law. Using Newton's second law, we'll be able to update the object's velocity and thus position as it moves. And through the energy principle, we know that the final amount of energy should be equal to the initial amount of energy in the system. The change in energy should equal 0 because energy is conserved throughout interactions. And we'll also be using these three equations to calculate kinetic, spring potential, and gravitational potential energy. I first uploaded the video of the mass into Tracker and tracked its center of mass. Tracker provided the position data based on that, and from that data, I calculated two important values, the spring constant and the spring's relaxed length. To calculate the spring constant, I used this equation, and to get the value of t, I found the average time it took to get through 3 oscillations. I found k to be approximately 6.88 newtons per meter, and from there, I calculated the relaxed length using this equation. I found it to be approximately 0.127 meters. After finding those two values, I created a computational model of the object's motion. I first changed the initial conditions to match that of the situation, and then computed the initial energies of the system using the equations to determine kinetic, gravitational potential, and spring potential energy. I edited the wall loop to calculate net force using the gravitational and spring forces, to update the ball's position and velocity using Newton's second law, and to update the spring's length and stretch. I also found the energy changes by finding the new kinetic, gravitational potential, and spring potential energies at the new position, and then subtracting the initial energies from them. When the program is run with a CSV file with the x and y position data, it looks like this. The red curve represents the change in gravitational potential energy, the blue represents the change in kinetic energy, and the green represents the change in spring potential energy. You'll also notice there's a yellow curve at 0 throughout the duration. This represents the change in total energy, and as energy is conserved throughout interactions, it remains at 0 the entire time, following the energy principle. So moving on to some other questions this lab poses, we can say that yes, the energy principle is satisfied as the change in energy remains at 0 throughout the interaction. Now to look at some estimates of oscillation periods, I estimated the periods of oscillation for both the x and y position data by finding the average of 4 oscillations. For x, I got a period of 1.662 seconds, and for y, I got a period of 1.496 seconds. This reveals it takes the mass about 0.2 seconds longer to complete one oscillation in the x direction than in the y direction. This discrepancy could be caused by the position in the mass's movement. As you can see, it moves in an elliptical motion that is wider than it is short. So this is why it would take less time to move